Select the major product of the following reaction. And so we are given a reaction, so we're given a starting material and some reaction conditions, and then we're also shown the IR spectrum for the product. So we could probably solve this if we're just familiar enough with this top reaction. So we have a terminal alkyne, and the conditions that we are treating this with is 9-BBN, that's 9-borobicyclononane, followed up with hydrogen peroxide and aqueous base. These are the conditions for hydroboration oxidation of an alkyne. And so hydroboration oxidation is a way to add water in an anti-Markovnikov fashion across a pi bond. And so what that means, anti-Markovnikov, is that rather than the hydrogen going to the more substituted carbon, to the less substituted carbon, and the alcohol going to the more substituted carbon, we see the reverse. So what we see here is we would get from that initial addition, so we've got 1, 2, 3, 4, 5, 6 carbon atoms, 1, 2, 3, 4, 5, 6. So instead of the water going to the more substituted carbon, we would see it add to the less substituted carbon, and we'd still have a pi bond there. And so this initially formed product is something that we call an enol. And so enols have that alkene and the alcohol attached to the same carbon. They are not stable. They undergo a tautomerization, which essentially results in this pi bond being moved and the hydrogen being transferred, although not quite like that. But overall, you're going to see the pi bond shift there to the end, which means the final product after tautomerization would be the aldehyde. And so the aldehyde is the product, but now that we've got this structure, we haven't done anything with the infrared spectrum. So let's take a look at the infrared spectrum and see if we can pick out what these key peaks are. So the type of peaks that we can see in an IR spectrum, we can see bonds to hydrogen, we can see triple bonds, and we can see double bonds. And we can see the single bonds as well. They just tend to show up in the region of the spectrum that's harder to interpret. So we need to know that on our IR spectrum, the top part of the spectrum is really where you see, in this area here, where you see bonds to hydrogen. In the next region of the spectrum, right around here, around kind of the middle, centered around 2200, is where you might see triple bonds. Right, so our product, or our starting material, we would have seen a bond there, but since the reaction has occurred and the triple bond is gone, we don't see any absorbances there. And this next region here is really where you'll see double bonds. Okay, so knowing that and knowing the structure of our product, we want to say, well, what sort of bonds to hydrogen do we have? Well, we've certainly got hydrogens all along this hydrocarbon chain. So those are all carbon hydrogens that are sp3 hybridized carbons. So where the carbon hydrogen stretch depends, where it shows up in the IR spectrum depends on what type of carbon it is. So we have sp3 carbon hydrogen stretches. And once you get familiar with those stretches, you will see that that's this cluster of peaks right here. Just below 3000 is where we see the carbon hydrogen sp3 stretches. Okay, but we still have these other things indicated right here in that bond to hydrogen region. So do we have any other bonds to hydrogen? Well, it might not be immediately apparent, but right here, we also have a bond to hydrogen. So we also have an aldehyde CH. And that's what these two peaks are. That's indicative of an aldehyde. So don't let the fact that there's two peaks and only one hydrogen throw you off. That's just because there's more than one motion that carbon-hydrogen bond can have. And what we're seeing here is energy of bond motion. So these are the aldehyde CH CH bonds. So the presence of these two signals would allow you to differentiate between C and B if you couldn't quite remember that this was anti-Markovnikov, for instance. Okay, and so in this molecule, those are the CH bonds we would see. In the product triple bonds, we would see none. And then in terms of double bonds, we've got a carbon-oxygen double bond. And so in that double bond region, there's only one absorbent, so we can pick that out as the carbon-oxygen. And these carbonyls are typically very intense peaks, so usually very intense, and that's because they are polar peaks, because you've got a lot of polarity between that carbon-oxygen double bond. And so that's because of the polarity. So we tend to see more intense peaks when our bonds are more polar.